In a series of 3 videos, I'm going to talk about the consistency, convergence, and stability of a multi-step method. The first video will address the consistency of a multi-step method. This is all primarily applicable to the Adams, Bashert, and Adams-Moulton methods, but as both Adams, Bashert, and Adams-Moulton methods are intrinsically consistent and intrinsically convergent and intrinsically stable, I've decided to use the example of something that isn't. So, first things first, we are looking at our classic initial value problem. dy dt is equal to some function fty, and some initial value of ya is equal to alpha. The numerical method to solve this has to satisfy the 3 criteria: that it's consistent with the differential equation, that the numerical solution is convergent to the exact answer of the differential equation, and the numerical solution is stable. In the notebooks in this folder, I'll illustrate these 3 things. So, as I say here, I'll give the definition of consistency, but I'll actually illustrate something inconsistent. Sometimes it's better to see something that isn't to understand what it is. So, the definition of consistency is a one-step method with local truncation error of tau IH at the ith step is said to be consistent with a differential equation if tau IH is equal to 0, where tau IH is equal to yi plus 1 minus yi divided by h minus h. And as h tends to 0, capital F tends to lowercase f. Yeah. This is true for both multi-step and one-step methods. But really what it's saying is, if we're approximating an equation, this part is our left-hand side, that's our dy dt. That's our right-hand side, our f. So capital F has to, in the end, be the same as lowercase f. If it's not, that means we're not solving the right equation. And that's where we come to the Abysmal Butler method. So it should look a bit like other methods. You have wi plus 1 is equal to wi plus h divided by 2. 4f minus 3f ti minus 1 wi minus 1. And we're going to illustrate this using the very simple linear differential equation y dash is equal to t minus y between 0 and 2, given the initial condition of y0 is equal to 1 and the exact solution of yt is equal to 2e to the minus t plus t1. Exact solution. We read in our Python libraries numpy for vector application. Math actually we don't need, but we'll leave in. Panda for the output, and then these are just for plotting. We define our function, our right hand side, which is fty is equal to t minus y. Very simply, we have it defined there. It's easy to change, and therefore this is very easy to adapt method. Now, as always, we start with our continuous interval and we discretize it. So h is equal to b minus a divided by n if we're interval from a to b. Here interval is between 0 and 2, so h is equal to 2 minus 0, and I'm going to do it for 40 steps, so divided by 40. And what we see here is 40 dots along our process here, and h is equal to 0.5. Now, as we know, the initial value problem has an exact solution. It's this nice little U shape here. Yeah? We set up our equation with our initial condition. W0 is equal to our initial value, which is 1. Now, our Abysmal Butler method, the general form is wi plus 1 is equal to wi plus h divided by 2, 4 times fti wi, 3 times fti minus 1 wi minus 1. For I is equal to 0, the system of differential equations is very easily transformed to w1 is equal to w0 plus h divided by 2 for t0 minus w0 minus 3 t minus 1 minus w minus 1. Now, Straight off, I've just changed f to be actually what's the right hand side. But what we have here is a problem. We don't know wi minus 1. We don't know this whole section here. This is an issue with any two-step method. You always have to start a step in. So we have to start as I is equal to 1. Now this is all reasonable. But we say have the same issue. We do not know what W1 is. Now, you can approximate W1 using any one-step method. It's generally advisable to use a higher ordered method than the method that you're using for the multi-step. So if I'm doing a two-step method, I should use a second order method. If I'm doing a three-step method, third order, and so forth. Here, as we have the exact solution, I'm just going to get W1 is equal to 2e to the minus t1 plus t1 minus 1. So I now have it set up again, where I have my initial values nicely set up. So here is our method. Very straightforward. We have our for loop, we input our function, we observe the method. And now the plot here shows this is the exact solution, that is the Abysmal Butler solution. Note that the shape of the solutions are quite similar, but they're off. Now, you could go, oh, well, that's an accuracy thing, because, you know, if the shapes are the same, maybe it's just that it's very inaccurate. It's undershooting here, overshooting here, undershooting here. Everything will average out. But it's not accuracy, it's consistency. So how do we prove that this method is inconsistent? To prove that the Abysmal doesn't satisfy, we have to show that TIH, yi plus 1 minus yi divided by h minus the right hand side, or capital F. That's what capital F is. We have to show as that tends to 0, that should be equal to f. But what we find is, as h tends to 0, 4 times FTI yi minus 3 FTI minus 1, that all times a half is equal to FTI yi divided by 2. So it's not there. So as h tends to 0, yi plus 1 minus yi tends to y dash, which is our definition of our initial value problem. So we have an inconsistency. Hence, as h tends to 0, we have FTI yi minus FTI yi minus 1 divided by 2, which is the same as FTI yi divided by 2, which violates the most important thing of consistency and is inconsistent. So we're not solving the initial equation, we're solving a different equation completely.